on low-rise structures. One, of course, we have mentioned this before, is resonance. That the design provisions for design for wind in buildings, low-rise buildings, let's say low-rise buildings, I mean, let's give this thing low-rise buildings must ensure that no resonance occurs. Okay, that is the prevailing wind frequencies must not coincide with any of the natural frequencies of the structure. That is, the prevailing wind frequencies must not coincide with any of the existing natural frequencies of the building. The other important consideration for low-rise structures is roofs must be well anchored to resist uplift. Okay, so if you have a roof building like that, okay, you got your elements there for the roof, got walls here. Sometimes the wind pressure within the building, and we might not look at this in this course, but we will talk a bit about this in the other unit that we are doing that is also discussing wind. Sometimes this happens that you have pressure built within the building depending on the direction of the wind and the openings of the building. So you could have positive pressure within the building, so it's trying to cause the elements of the building to bulge out, and when that happens, then you could have this roof wanting to fly away, and because of that, therefore, you need to ensure that this has to be well anchored. You have had many stories about buildings. Let me write here: positive pressure, internal pressure, due to wind. You've had many stories where there was a significant gust of wind and the roof was simply just harvested or lifted from the building and deposited elsewhere. So this is something that one needs to check carefully when considering wind in low-rise buildings. The other item that is important to consider is that the cladding units have got to be properly fastened. Including roofing sheets, etc. must be properly fastened. Okay, we did discuss a little bit of this in a previous session, and then the fourth one. In the event that roof trusses are used, stress reversal, and I'll explain this shortly what it is. Stress reversal must be checked and provided for. Okay. We forgot to put today's date here. Let's put today's date here. It's 25th of September 2023. Okay, and we save that. So when you have a roof that is, when you have a roof structure that is made of trusses, you have a roof structure that is made of trusses, say something like that. You find that under gravity loads, so gravity loads, so you get a, for truss analysis, if you can remember from the assumptions for trusses, is that trusses do not carry bending forces, so they're only loaded at the nodes because they only carry axial forces, that is tension and compression. So under gravity loads, the truss would mainly have the bottom chord under tension and the top chord under compression. And internals will carry the shear and would therefore, not the shear as such, would mimic the shear capacity of a beam and therefore would be alternating tension and compression. So let's not look at the internal elements. Let's look at the external elements. Let me write this nicely so that when you revise, you can remember. So, element under compression. That element and that element, they're under compression. And this, the bottom one, bottom chord, top chord, bottom chord, under tension. Now, what happens is, it is possible that under certain conditions of wind velocity and wind direction and openings in a building, as we have said in this case above here, number 2, it is possible that instead of the roof being loaded downwards by gravity loads, it be loaded upwards by wind loads. So we've said this blue represents gravity loads. If it so happens that we have positive pressure within the building, then it could happen such that the roof is now, the pressure due to wind within a building is trying to lift the roof. It's trying to lift the roof. Okay, so we've already talked about one possible failure area as the joint between the roof structure and the rest of the building. The other element that you need to check carefully is when you have the wind exceeding the gravity loads. When this exceeds gravity loads, the top and bottom chord would change. To tension and compression respectively. Such that now instead of the truss bending downwards, it's now trying to bend upwards. So the bottom chord now is under compression. So what's the problem with that? You remember that tension elements would predominantly fail by yielding. Okay, so this bottom chord would be designed to fail by yielding, which is a much higher load than if it was to be checked for failure by buckling, which would happen when you have that stress reversal. And this then would be a big problem because you have a long element. You have a long element. Long element which would need to be checked for buckling failure under stress reversal. So it could buckle. Under stress reversal, this element is being compressed. It could buckle out of plane. Okay. So these four are the main ones that one would need to think about if you were designing an element or if you're designing a roof, low-rise roof, and if you were to consider winds. For wind, I want to stop there because we don't want to dwell too much on that at this point. I want to pause and allow if somebody has a question or a comment on this one before we proceed. As I've said, the other unit, the lateral nodes are the main thing. So we have opportunity and time to discuss a little bit more here because we have a whole array of things we need to discuss. So we touch on what is relevant to the low-rise structures, and we then proceed. Anybody with a question or a comment on this one before we proceed? I want to move to seismic loading and make an introduction as well. Great. So if we don't have a comment or a question, I will now move to seismic loading. Seismic considerations. Now, when you think earthquakes, earthquakes are basically the movement of the ground. So how does the movement of the ground generate a force on a building? Isaac Newton says a body sorry about that. So Isaac Newton says a body continue in at a certain speed and in a certain direction unless compelled to do otherwise by an external force. So we have buildings that are static. They're not moving, they're just standing there. And then the earth decides to move. The building doesn't know that the earth has decided to move. So what does the building feel? It feels forced to move with the earth. It feels forced to move with the earth. That force it feels is a form of an inertia force. So earthquake forces are basically inertia forces on buildings. The building doesn't know the earth has moved or is moving, and the earth is moving. So the building is forced to move with the earth because it's attached to the earth. This force is very similar to if you're traveling in a vehicle, for example, traveling on a straight road, and then you go onto a curve or into a curve. Then what do you feel? You feel like as if you're being pushed out of the straight line because the vehicle is now doing a curve and you want to continue going straight. The vehicle is doing a curve and you want to continue going straight. So it's the same concept. It's an inertia force. Okay, what we call centrifugal and centripetal, if you can remember from your secondary school physics. So as an opening statement, we can say here that earthquake forces on buildings are basically inertia forces. Now, for us to determine how much force this building feels or the other building feels, there are few important considerations that we need to bear in mind, or we could say factors that do affect the amount of earthquake force that the building experiences. And I will mention them here for the sake of mentioning them. So you said earthquake forces are inertia forces. The earthquake force that we can allow or we allow on a building, the earthquake force that we allow on a building during design is a function of several things. One, the type of structure. Of the building. So generally, there's a whole array of structural types and structural systems that we use to resist lateral loads. The simplest of these and the weakest of these is what we call a load-bearing structure. Basically, a building that sits on structural masonry walls. And you guys have been trained on masonry, so you understand when I talk about structural masonry walls. So this is the simplest, most basic. it is limited to maybe up to 4 levels or something like that. It's a very basic structure. Then above that, we have something we call an unbraced. Let me just list them. We will not talk too much about them, but it's good to. So you said load bearing. Masonry structure. Then we have unbraced frame structure. Then we have braced frame structures. The unbraced frame structure is a structure that comprises of beams and columns, and it does not have any element within the building to stiffen it against lateral forces. Such elements that stiffen buildings against lateral forces are elements like shear walls. And a good example of the shear wall is the bell-bottom building just neighboring us here in town. You see the bell-bottom building on the sides, you see it has got solid walls from the top to the bottom and into the foundation, to the foundation level. The solid reinforced concrete walls, I think they are 400 thick or something. Very, 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 very solid walls. So those walls, the purpose is to stiffen the building in that direction. So when the earthquake occurs in that direction or wind is blowing in that direction, these walls, they take the bulk of the lateral force. So if a structure is equipped with that kind of a wall, then we call it a braced structure, frame structure. So the bell bottom is a good example of a braced structure. Let me write here, e.g. the bell bottom. If a structure has not been equipped with these very strong reinforced concrete walls or cross bracings for steel structures like water tank towers, the ones that they build nowadays out of structural steel, you see they have cross bracings all through. So that's a braced structure. Now, if a structure is not equipped with this, either shear wall or a set of bracings like in those elevated water tanks, we call them unbraced frame structures. A good example is this is the U block, where we sit. Okay, it's an unbraced structure. It's a short structure. It doesn't have lateral load resisting elements because the earthquake forces are not big, and therefore it is an unbraced structure. There are a few other structural systems that maybe we might not be able to mention here. But the first consideration to how much earthquake force a building will feel is the type of structure of the building. Okay? As the structure becomes more rigid, the force of earthquake that this structure will experience in the event of the ground motion increases. That's why the type of structure is important. The second consideration, which is important when we are calculating earthquake forces, is the use of the building. We are saying, how important is this building? If this building was to collapse in an earthquake, what kind of losses would be incurred in terms of human life, in terms of property, etc., etc. So as the building becomes more important in this aspect, you find that the earthquake force that we allow for that building in design becomes bigger. So we become more generous in terms of the provisions we make for earthquake for that building. Let me just paint a simple picture. If you are designing a 20-story building here in town, or if you compare this with a maisonette that you're building in your village, in your shamba there, and your neighbors are hundreds of meters away. If an earthquake was to damage your maisonette in the village, the loss to property and human life would probably be limited to you and your things within that maisonette. But if a 20-story building in the town center was to collapse due to an earthquake, not just the contents of that building and the occupants, but also the surrounding large area, many meters radius, buildings would probably be destroyed, and property and many, many people would be injured and killed. So this is the concept of the use of a building. I will discuss it a little bit more when we discuss the high-rise structures. But this is the thought, and you find that most earthquake standards, I think all the earthquake standards for structural design that I have looked at or seen, they take this into consideration. It's an interesting consideration. We will discuss this in the other unit a little bit better. The third consideration, broad consideration, is what is the probability that an earthquake will actually occur in the area where you are designing this building or where you intend to put up this building. So what is the probability that an earthquake will occur and next to this we are asking what is the probability that an earthquake of a particular intensity will occur. So here in Nairobi, we have had earth tremors. Earth tremors. So there's a certain intensity of earthquake that is very mild. Okay, so a lot of times you wake up in the morning and you hear maybe in the news or TV or radio, they say there was a tremor at midnight or at 2 a.m. in the morning. But it was so slight that, or so small that you were able to sleep through it. Sorry guys, I had lost a connection. So we were at this point where we were saying, for example, here in Nairobi, we do experience very slight tremors, and sometimes they're so slight that they occur and we don't notice. So we only hear about it either in the news or we hear people talk about it. There was a tremor in the evening yesterday or something like that. There are places where the intensity is so much that when an earthquake occurs, you will not miss to have buildings coming down, properly designed buildings for earthquake. For example, last year there was a place where, I can't remember the name properly, unfortunately, very, 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 very high intensity earthquakes occurred, and there was a lot of loss, a lot of buildings collapsed. So if you were designing for a building for earthquakes in that area, the question would be, what is the probability that an earthquake and an earthquake of this or that intensity would occur there? So you go back to history, what has been recorded. We'll see an example of this in the other unit for high rise. So you go back to history and say, what is the history of earthquakes in this area? And what are the intensities? And then, of course, using statistics again, you would then be able to predict and say, so generally, an intensity, and earthquakes of intensities of this magnitude are likely to happen within the next 50 years or 100 years. So if your design life is 50 years, then there's a probability that a certain earthquake intensity will occur, and therefore you design for it. So you cannot pick that intensity and come and design a building in Nairobi for that, because the building will be unnecessarily strong for an earthquake that will probably never occur. So the key word here is probability. So these three considerations are the main considerations. There are many others, but these are the main ones that would go into the thought process when we are trying to design for earthquake structures, so buildings to resist earthquakes. I want to pause here for the thoughts on earthquakes, so that I allow you to, if you have a question or if you have a comment, you can ask. I've just done a very, very, very light overview of for earthquakes, so that we can go into the other items that we need to cover in this course. Any question, any comment? As you're saying, we have opportunity to really delve into these two lateral forces in the other unit. There's enough time for them. So anybody who is interested, you could step in and join in the conversations there. I think these are important and interesting items if one intends to go on to become a structural engineer. Okay, any question, any comment? Great. Yes, Elvis wants to say something. Elvis, please proceed. Yes. Correct. Okay, so that's a good question. I've just mentioned this in passing, but if you look at any of the standards for earthquake forces buildings, they talk about, there are several considerations to say how important a building is. Of course, the first one and the most important is human life. So you'll find that the structures that are likely to house many people, for example, places where people are likely to congregate, like schools, like public buildings, things like that. These usually will have a very higher categorization in terms of how important a building is. The other thought that goes into this is issues of security. So if you're designing a building, for example, for occupation by, say, the police or the armed forces, so these are security issues. Such buildings also would feature very highly in the categorization for the importance of the building. So there are several thoughts that go into it to decide how important a building is. I've just given us a very simple example to say that just thinking of the human life only, the building that is in the town center and it is big, if it was to fail under an earthquake, the loss to human life would be much, much more than, let's even consider the same building, but is out of town completely. Okay, so the loss for the building that will be in town will be much higher than the building that is not in town. And I don't like giving examples of the tragedies that we've gone through, but the Bell Bottom again, when it was attacked, the loss and the injury, extreme injury, people lost limbs and eyes, the people became blind, and those stories are available in the media. You can check the trauma levels. People who somebody came to this office where I sit now last week, and he told me there were students here when the bomb blast occurred. They were jumping from sorry, it seems like my internet is a bit unstable. So I'm telling you, a gentleman came to this office recently. He wanted us to sign some documents for him. He's a former student of here. So he was a student when that occurred. And he was telling me they were actually jumping from first floor. There was no time to go through the staircase. Okay. And that kind of thing, it doesn't leave your mind. These are traumas that remain with you for the rest of your life. So then we are asking how important this building. If this building was, for example, to collapse in an earthquake, what would be the price that we would pay as a country? I will also mention, now that you've asked, another category is there buildings that are symbols of national pride. For example, the KICC. So if anything was to happen to the KICC, it's not just, human life, we cannot put a price on it. So that would be part of the loss. But even our national pride would be hurt, because those days when we were small, when I was a small boy, and when you came to Nairobi, the proof that you were in Nairobi was to take a photo at the KICC. Then you would show your kinsmen and your natives and say, I was in Nairobi and I have a photo at the iconic. So you see, the importance has got many considerations that go into it. And maybe we will talk about this a little bit more. I don't know if you're part of the group that we are discussing the high-rise buildings. That's okay. If you like, you can just step in. Even if you're doing another option, you can step in and listen to the conversations and be part of them as we discuss, because I think is interesting. Already we have some other students that are not doing this unit that requested to join in, and I think the more we are, the more interesting the discussions. I hope this helps a bit with the question. Now I want to move to a different topic. Okay, so I want us to now move to discuss retaining walls. This is one of the topics that we need to cover here. I want us to discuss this. We just discuss the overall thoughts, and then we go and do a sample calculation of a design of a retaining wall. So we'll dwell quite a bit on this topic for this unit. Okay. So we can close this this one leave so that we are left with retaining walls. Allow me to clean this up a little bit. So we had used it last year and it's a bit dirty. Just give me a moment. I'll give you these notes and the scribblings and everything I'll give you. But it's also prudent as we discuss. I notice there's a lot of students who just scribble their own notes, which is also a very good thing, so that you have a better record than what I might be able to give you. You see, when you write your own notes, it helps you to remember better when you are doing revision. So you can be writing your own notes, but I'll give you these notes. They're basically prepared for you. Just a moment. I think we're just about to get to the end of this. We have to write our own this one, so I'll just remove it. Sorry, I should have gotten a clean document before. I'm seeing it's heavily written on. Not good. I need to do all this. So just create a new. Let me create a new one that is clean. Okay, so let me create a clean one for you. Just file, print. Low rise. Perfect. So a retaining wall is a structure that holds back soil or rock from a building, a structure or near an area. Trying to think what is a good example of a retaining wall near here. Okay, so if you go on Thika Road, there's a lot of overpasses and underpasses. For example, if you go to a good places where, say, Allsops. Allsops is a place where the road to Thika goes under an overpass. There's a retaining wall there, and slightly further ahead, as you come up before you go on the flat to Kasarani, again, there's some huge retaining walls there. It's huge reinforced concrete walls that are basically holding back material from falling onto the road. So any structure that holds back soil or rock from a building, a structure, or an area is a retaining wall. Retaining walls prevent downslope movement or erosion and provide support for vertical or near vertical changes. So we have mentioned this rod, this thicker rod. So you got a wall there. Got another wall there, because they've got foundations of some sort. And we'll look at this a little bit to detail. So then you have another road surface there. You have another road surface there. And you have retained earth here. Got retained earth here. Okay. So you've got a road surface, another road, so it retains material. Cofferdams and bulkheads, structures that hold water, are sometimes also considered retaining walls. So if we have a structure that holds water back, it could also be considered as a retaining wall of some sort. But we'll look at this a little bit to some more detail. Now, retaining walls are generally made of masonry, stone, brick, concrete, vinyl, steel, timber, and I want to say etc, etc. This list is not conclusive. etc. Designers and material scientists are coming up with new materials, on a daily basis. So this list cannot be conclusive by any standards. Once a popular and inexpensive retaining material, railroad ties have fallen out of favor due to environmental concerns. So you see these railroad ties, these things that what they call sleepers. They have also been used as a material for retaining wall before. So you see, the list cannot be conclusive, because we are very innovative and we keep seeing opportunity in using different materials to retain material. Segmental retaining walls have gained favor over poured in place concrete walls or treated timber walls, as they are more economical, easier to install, and more environmentally sound. We'll look at these shortly, types of retaining walls. The most important consideration in proper design and installation of retaining walls is that the retained material is attempting to move forward and downslope due to gravity. So if you have a retaining wall, it's retaining material and material there. So this, you have retained material. What happens is that this material that is retained here is trying to move forward and downwards. Okay. So it's trying to do this. Okay. Forward and down slope due to gravity. That's the one there. This creates lateral earth pressure behind the wall. Okay. So the wall feels pushed. The material is pushing the wall. That's what we are referring to as lateral earth pressure. And we will look at this to some good detail. And we'll discuss how we calculate that lateral earth pressure. But you'll remember from your soil mechanics that and that. Angle of internal friction, phi, and the cohesion of the soil. Cohesion of the soil. This we will look at to some detail slightly later in this discussion, and how they affect the push that the retained material is pushing the retaining wall with. The retained the retaining wall could also decide to move under this retained material pressure. The retaining wall might move, and we'll look at some detail of what are these possible movements that this wall could have, because when you design the wall, you need to be able to ensure that these movements will not occur. It's part of the design calculations. Lateral earth pressures are typically smallest at the top of the wall and increase towards the bottom. Earth pressures will push the wall forward or overturn it if not properly addressed. We will calculate all these. Also, any groundwater behind the wall that is not dissipated by drainage systems. We'll look at drainage systems as well. All this we'll cover in this topic. Cause an additional horizontal hydrostatic pressure on the wall. This is a very interesting thought. And we'll put numbers to it, and then you'll see how much difference it makes just to drain the wall or not to drain the wall. Say makes big difference. We'll put numbers to that, and then it will become very clear. As an example, the International Building Code, the IBC, International Building Code. I don't know whether this is the current or the UBC is the current. One is the predecessor of the other one. Probably you haven't come across this, but there are two codes that are almost similar. One is the predecessor of the other one. There's a Unified Building Code and there's the International Building Code. I think the Unified Building Code might be the newer of the two. This code is available online. The PDF is available for free online. If you guys are interested, you could look it up. It's a very huge document. It's not the kind of document that you read from end to end. You only get it and you use it for reference, not for reading page by page. So if you find something that you need to know how it is done, then you go to that particular section and only read those few pages. It's a huge document. I think it's like 600 or more pages, something like that. Requires retaining walls to be designed to ensure stability against overturning, sliding, and excessive foundation pressure. We look at this. Those three we'll look at a little bit more carefully. And of course, against each of them, different standards have got different factors of safety to ensure that they don't happen. But this International Building Code requires that you have a factor of safety of 1.5. We'll look at some detail on that. But before we go into those calculations and we try to make sense of these statements that we've read, it's good to know what is available in terms of types of retaining walls. So this is what we want to look at in this section 1.2 of this topic. So the first type of retaining walls is gravity retaining walls. Gravity walls depend on the weight of their mass, that is either stone, concrete, or other heavy material, to resist pressures from behind, and will often have a slight buttress setback to improve stability by leaning back into the retained material. So if you're doing a gravity retaining wall, you want a heavy mass. You want a heavy mass. You want a big material. So this is retained material. And basically, you have a weight here. And this wall, this material, of course, we've agreed that it's pushing that way. It's trying to cause this wall to move. So what is causing the wall not to move is basically that force there. Let me use terms that you are used to. So let's say the weight of the wall is R, is a reaction downwards. So the force that resists the wall from moving is simply mu r, and mu r, you guys, you know, because you did you calculated friction forces in your secondary school. So these are gravity retaining walls. For short landscaping walls, they are often made from mortarless stone or segmental concrete units, basically anything that you have that could be heavy. So these short walls, you could do that. Dry stacked gravity walls are sometimes flexible and do not require a rigid footing in front areas. Earlier in the 20th century, taller retaining walls were often gravity walls made from large masses of concrete. Okay, so this you read for yourself, but what is important is that these retaining walls are no longer very popular, except for their use in dams. Okay, these walls are no longer very popular, except for their use in dams. So we do have gravity dams, like a lot of the dams that we have done in the last few years have been gravity dams, and going forward, most probably we'll continue doing gravity dams. It's not my area. I will not talk a lot about it, but most of the dams that we are doing, even the ones that were stalled recently, the Aror, the Kimorer, the Kurisoi, all these were gravity dams. They were going to hold back water, which is a retained substance, by just the sheer weight of the materials of the dam. Okay. The main disadvantage is that they take a lot of material. Okay. The main disadvantage is that they take a lot of material, which is not economical. So that's why. Yes, somebody wants to say something. Hello, someone is saying something. Oh, maybe they switched on their mic by mistake. Okay, so the other type of retaining walls is what we call sheet piling. So you've got thin corrugated sheets. So you corrugate them that way. Thin steel sheets. So you give them ridges like that. So this sheet would be like what? Maybe 1.5, 2 millimeters, for the sake of this discussion. Okay, let's assume it's 2 millimeters. If you had it not corrugated like that, let me show you why corrugated. There's a sheet like this. So if you try to hammer it and it's not corrugated, you try to drive it in the ground, you'll not make progress. If you corrugate it, you give it some folds. Fold it. Give it some folds. Then it becomes stiff. So you can actually apply some force, hammer it into the ground. So that's why these are corrugated. Okay. And this kind of retaining wall is usually applied on ground that is very soft, so that then you can just hammer it. So you bring the sheet and you hammer it into the ground, and you fit another one and hammer into this. So you form some form of temporary or not very permanent retaining wall. If you can remember from your strength of materials, if you want to know the science of what is happening and in that stiffening, if that was XX, then this element would have a higher IXX than this element. Okay, from your strength of materials. So that's the other type of retaining walls. You can read this small paragraph we put there in your notes. And then we have cantilever retaining walls. This is the commonest retaining wall that you find nowadays. Like what I've referred you to, the ones on Thika Road, they're basically cantilever retaining walls. And they take the form of an inverted T. They take the form of an inverted T. So you got a foundation. Okay, so these walls are this way. So that's retained material there, and you got your wall in that manner. We will actually do an example analysis and design of this wall, so you get a feel of what goes into the design of a retaining wall. But these are the commonest. This is the kind of that we got almost in a lot of places on Thika Road. Some places there are different type of wall, which we will discuss. I'll introduce later. But this is pretty common. They're usually made of reinforced concrete. Okay, it's made of reinforced concrete, and it's basically a cantilever that way. So we analyze and design it like an inverted cantilever. Okay, so it's being loaded here, and it is fixed at the bottom. We'll run a design on that, and then it will become clearer. Okay, this retaining wall is efficient in material, so you don't need a very thick element to get it right, but it requires well, all retaining walls require good design. Recently, not many months ago, I sat in a panel for that we were looking at a case where a retaining wall collapsed, and this retaining wall was designed as a cantilever retaining wall, but the engineers involved did not design it. They just picked some design and they specified. And unfortunately, this wall was a bit tall. It was a bit tall. It was about 7 meters. Okay, this wall was about 7 meters. Of course, it was a disaster, and as it collapsed, there's unfortunately two people who were working on that site. They were killed, and it became a big issue. So these are very efficient walls, but they require that one does a proper design, and then you size it properly. You do all the checks so that once you specify that this wall, this is how I want it built, then it is built that way. The other problem of that wall that had collapsed is that so it was not designed. So it was under-provided. Then when it went to site, the site people in their wisdom also reduced the foundation size. So what was in the drawing, which was not adequate, the fellows on site went ahead and also chopped off some of the foundation to save material. So it was a really, really poorly done wall, and of course it put a lot of people in trouble. You see, if you're the designer and something like that happens, and your name is in that project, it becomes a murder case. So DCI is involved. They charge you for that. So it's really a very scary place to get to. But they're the commonest walls currently that we do for retaining. Then we have the anchored retaining walls. So sometimes you're not able to achieve a good depth for this wall, this retaining wall that we have just talked about here. So the general requirement for this sheet piling is that if you are doing sheet piling, you have to have these dimensions that if this is H, then this should be 2H. a third above ground, 2/3 below ground. So it's got to be hammered into the ground a significant chunk. Sometimes you're not able to do this. And if you're not able to do this, there is an option of tying back this wall. So you tie it and you bury an element like that. Let me use a different color. So there's an option of tying back this retaining wall. So you tie it and bury an anchor of some sort. And this anchor is referred to as a dead man. Okay. Now, if you do that, then you have an anchored retaining wall. Okay, you have an anchored retaining wall. Then, of course, we have the gabion meshes that have been many years. Where have I seen gabions this side? Anyway, you guys, you know gabions. If somebody doesn't know gabions, you create boxes using wire mesh, and then you arrange them. And you fill them with stone, and then you create another box of mesh, and you fill stone. Then you create another one so that they are stepped. I think if you search, for example, on Google, you see a lot of images of gabions. Gabions made of mesh cages. Okay, they are all the design of retaining walls, but they have to be sloped. You cannot do gabions vertically like that. So you got a gabion there. No, you got to step them. So you got gabions here. You've got another one overlapping there. So they are stepping like that. Again, they've got to be properly checked for design. If not, they have a tendency to fail quickly. I was somewhere on Friday, and I should have taken photos of those. Somewhere I forgot. They've started doing the gabions. Let me see if I can ask for a photo, and then I could even put it as part of these notes. I could insert it there for your reference. And then we have segmental retaining walls. Now, if you go to still on Thika Road, you will find that there are some areas where they have done retaining walls, but they're basically just blocks. That seem to be arranged, and they seem to be retaining, to be holding back the material. These are what are referred to as segmental retaining walls. And the trick is this. So you have a wall. So you have a wall. That is made of blocks. You've got a road here. So you've got one road there, you've got another road there. They've done this a lot on Thika Road. You've got a road there, you've got a road there. Maybe use a different color. Make it clearer. You've got a road here, got a road here. There's retained earth. You've got retained material here. So what you do is that you tie these blocks. They are tied back by some material. They're tied back, so they're tied back into the retained material. So before you put the retained material, you put the block, you lay the tie back, and then you put the retained material and compact, and then you put the next block, you tie it, you put the material for tying it back, and you compact that layer. So it's done in layers like that, until you have your wall. So this wall, this stone, this block is not able to fall off because it's tied back. And this material is what is called geosynthetics. This is geosynthetics. It's a material that is designed to be able to provide anchorage within ground, amongst other things. On this image here, there's that material there is a geosynthetic. It is possible that your lecturer for either foundation engineering or for soil mechanics might have samples of this with them. So when you meet them, please, you could ask them if they have a sample of a geosynthetic material. They could show you. Unfortunately, I don't have any with me because this is really work for geotechnical engineers. So the lecturers that teach you foundation engineering, etc., etc., these ones they could have this material. But if I come across one, I could share it with you. So this material is the one that is used to tie back this block, and it's compacted. Then you place the block, tie it back, you compact. You place the block, you tie it back, you compact, like that. So that's a segmental retaining wall. And there's an image here that I've put, but it's not very clear. Maybe I'll put an image of thicker rod, because this is what is common with you. You can relate with. You can walk there and see the blocks. Anytime you travel that way, you can be checking that. Now, we have mentioned that the force that pushes the wall depends on this pressure, depends on the characteristics of the retained material that is the cohesion of the soil and the internal angle of friction of the soil. So if you can modify any of these two, you can actually change the amount of force or the amount of pressure that pushes the wall. I'll repeat. How much force is pushing the material pushes the wall with is dependent on the property of the material. And we've mentioned that there's the cohesion and there's the internal angle of friction. So if you can modify these properties of the retained material, you can actually reduce the amount of force that is pushing the wall, and by extension, therefore, the design, you can reduce the design, you can make the design lighter of this wall. So that's what I want to talk about briefly before we wind up this session. So sometimes we want to strengthen the soil. We want to strengthen the soil. So basically, we want to increase the cohesion. We want to strengthen the soil. We want to increase the cohesion of the soil. Okay, so that's what we want to talk about here. That is, increase the soil cohesion. The force experienced in a retaining wall from a retained soil is dependent on the cohesiveness and the internal angle of friction of the soil. We've just said that. In the event that the loads imposed on the retaining walls are big, for example, if you find that you're doing a very tall wall, like this story I gave you of the 7-meter wall that collapsed, one of the ways of dealing with it, of course, you could have made the wall as strong as possible, but the other way of dealing with this kind of wall is to try and moderate the force that will eventually wind up pushing the wall. And one of the approaches is to modify the cohesion of the soil. So that's what this subtopic here we will deal with. How can we improve the cohesion of the soil to reduce the force on the wall? Okay. The force experienced on a retaining wall from a retained soil is dependent on the cohesiveness and the internal angle of friction of the soil. In the event that the loads imposed on the retaining walls are big, such can be reduced by modifying the cohesiveness of the soil via stabilization. Okay. Some guys outside the office, they're making too much noise. It makes it very difficult to have a meaningful discussion. I think let's deal with this in the next session. Okay. Let's continue from there next week. Some people are just idle and noisy. It's even pissing me off. Okay. So any question up to that point? Any question, any comment before we wind up this session? Great. So let's stop here for today. We will continue this discussion in the next session. Thank you very much.